Добре дошли и добре дошли на PlovDev 2022. Обръщаме внимание на последният клип. Това е Desk Buddy, смарт решението за управление на хибридни офис пространства и първият продукт на ProxyApp. Повече за него не забравяйте да научите в нашата будка на ProxyApp от самите създатели. Сега нека да продължим с следващия лектор, който всъщност ще бъде и последния гост лектор за нашето събитие. Това е Виктор Пахучи. Искам нещо да кажа за него. Значи, той отново е гост-лектор от чужбина, от Украйна. Той ни сподели, че родният му град е Харков и последните месеци, заради обстоятелството в войната, той се е преместил в някой друг съседен град при някои негови роднини. Не разбрахме с голяма точност. Нещо, което разбрахме от него вчера вечерта е, че са имали нови атаки в града, в който се намира в момента и няма да има възможност да се включи на живо в нашата конференция. Все пак ние бяхме подготвили бекъп варианти и бяхме помолили всички наши лектори да запишат своите презентации на видеофайлове, така че сега ще уважим Виктор и ще му пустим неговата презентация, неговата лекция, по-скоро цялата му лекция на повторение. Единственото, което ще бъде минус за вас е, че няма да може после да ви отговаря на живо на вашите коментари. А сега нека да обяви Виктор. Виктор Пахучи, той е с над 5 години опит в работата си с Go, работи по проекти в консултантска, финтеч и автомобилната индустрия. Освен това участва и в редица Go събития в родният си град Харков. Той е подготвил вълнуваща лекция на тема Go Escape Analysis. Пускам лекцията на Виктор и ще се видим веднага след нея за обявяването на интересни неща. Стойте с нас и до скоро!
My name is Viktor and I'm a Go engineer at Intellias. I'm so happy to be here, thanks for that, and hope that the next 40 minutes will be interesting to you. So I want to talk with you about escape analysis, and let's take a look at our agenda. We will make a quick overview of Go memory kinds. A part of that, obviously, we will learn what escape analysis is and what its rules can be useful in our job. Go applications memory consists of a few different segments. Some of them store program source code, other global constants, etc. Such segments that aren't important for us today are marked as dots. We have to focus our attention to two of them, stack and heap. Let's start from stack. It's a segment where temporary variables created by a function are stored. It mostly contains methods and local variables, including function arguments also. Like in Java, for example, each thread has its own stack, each Go routine has its own stack as well. Alright, first interesting point to us is that stack has only 2 kilobytes. Been changed many times since the release, right? But now it's only 2 kilobytes only. Thanks to that in Go, we can have tens of thousands of stacks and it's fine. Another point that I want to mention is that stacks can grow. That's obviously right. If we start from 2 kilobytes, then we should have a possibility to grow, right? And it can grow up to 1 gigabyte in 46-bit systems. Also, when we know that it can grow, the question is if it can shrink as well. It can, even more. It happens automatically when the function execution ends. To be more accurate, it freezes when a new function requests the memory. Yeah, but you can read about it later and to find much more details about that. Let's keep it. What is interesting is that garbage collector involvement isn't needed here. Please keep it in mind. So stack is cleaned up automatically, right? Good. Moving to heap. It's used for dynamical memory allocation. For example, all global variables are stored here, and that's one of the reasons why we shouldn't use global variables too often, right? Moreover, some types like structures, maps, and other complex data structures may be stored on heap as well, and we will take a look at these scenarios in a later slides. As well as huge and even bigger than the amount of available RAM on your system, thanks to virtual memory we have, right? Unlike stack, it's not cleaned up automatically. It requires garbage collector involvement, GC. And that's very important to us. Please keep it in mind also. The last but not the least is that we can somehow control its size. I don't know if you're aware of it, but in Go we can't manage memory directly. I'm not ready to say is it good or is it bad, but it's our reality, right? Despite that, we have a mechanism that tells us how often to run GC. So as you can see, Go GC and set GC person function from runtime package, we can use them. I'll explain it a bit more later. Okay, so as I've said before, we have a GC. It's concurrent, recolor, mark and sweep, garbage collector. To make a long story short, it's concurrent garbage collector. That's the only important fact to us, right? So let's say Big Brother is watching you. Yes, GC is always there. It's always working, and we have to remember that. So please recall that GoGC variable we saw in the previous slides, right? It's the only configuration we can do. Just a few words about its workflow, right? Well, let's imagine that we have a simple application that uses 100 megabytes of memory. That's a black square that you can see on this slide, right? Our GoGC default value is 100. This means that GC shall be run before the app meets 100% more memory than it uses right now. So, after all, it's 200 megabytes in our case. That's a red square. Let's say that we can somehow specify how often garbage collector should be run. Trust me or not, that's it. Like, that's the only option we have. There is no YAML configs or any other tools for that, right? So that's what we have in Go. And we already know that GC exists and we know that it's always working. So let's review some scenario. Please pay attention to this picture. We have a simple scheme of Go runtime scheduler here. M is OS thread, G stands for Go routine, and P is some kind of abstraction layer that is responsible for matching G and M. I'm trying to avoid any complexity here related to this scene because we are still focused on escape analysis topic and performance optimization, but not on concurrency itself. Alright, here we have a presentation of the system where 4 threads are available to our application. And let's assume that we have 4 ongoing Go routines and some pack of work, I don't know, any computations. The main idea here is that in general, our garbage collector takes 25% of our resources for itself. As you can see here, it's mentioned on the picture, right? So 25% of our resources. There is no free heap cleanup and Go. That's very important to us. This means that if we have 4 threads, and since that our application can execute 4 or at least 4 our business-related Go routines simultaneously, we are on, so we can execute them at the same time. Moreover, in cases if during garbage collector cycle we produce a lot of allocations, garbage collector can make a decision to ask additional resources for support, right? So in some cases, it may take even more than 25% of your resources, right? So you should understand that it may be even more. It can take 2 threads to work only for garbage collector, and only half of them will be available to you. So small summary, garbage collector is expensive and heap cleanup is expensive as well. Yeah, small reminder. Before going to escape analysis itself, I should recall that everything in Go is copied. So whenever you pass any parameter to your function, it will be copied. In case you pass a pointer to something, it will be copied, sorry. Yeah, so we copy everything. Finally, escape analysis. It's a process that, let's say, compiler uses to decide where values of our program should be stored. In other words, we can understand when memory will be allocated on a heap, not on a stack. Because by default, it should be allocated on stack. How does it work? Yeah, so Go builds something very similar to a graph, taking every allocation statement as its root. By allocation statement, I mean different ways of variables declaration or any values initialization, let's say, right? So any var, make, new, etc. Then it analyzes the referencing and addressing operations. The referencing is when we are taking a value to what pointer points to, and addressing when we are taking a pointer to some memory value. -1 and addressing it's +1. Please take a look at example in the right side to understand the logic here. Yeah, you should see this. So just to understand how does it work. After each variable with negative count is candidate for allocation on the heap. What is important? Just candidate. So it shows only candidates, and the final decision can be made based on different information, and we will see later, because just a candidate, keep it in mind. I hope that is clear for you. Okay, escape analysis output. So it's time to learn how to run this tool. Please take a look at this console image, right? Here we have specified GC flags with -m equal 1 and -l. That selects level of output detailization. -l means that we want to turn off functions inlining. If you are not aware of what it is, like, I recommend you to skip it, but even better to read about it. It's a technique when small function's body can be, let's say, copied and executed in the function of its caller. So we're just taking a code of function we want to call and executing it in the function where we wanted to make a call. I hope that's clear, right? But anyway, it will be interesting for you to know more about it if you're not aware with it. So anyway, this allows to avoid additional calls, data copying, allocations. It's also very important performance optimization technique. But we don't need it to be turned on while we are doing escape analysis. For more info, you need to check the documentation and find some corresponding articles, I guess. Okay, so right now we select the most generic answer because we're using -m equal 1. Here another example. We are like, the only changes is -m equal 2. And because of that, this time we have a bit more detailed information, including explanation of my decisions, right? As you can see that. And we can move it even more, and by changing it to m equals 3, we can receive even more detailed output. However, second level almost always is sufficient because, again, you still see the results there and still see the rules there. But anyway, you even can go more to -4, but I will not show it to you. Okay, so let's review the first case. First of all, please pay attention that all my code examples will be somehow simplified to not take out space. So maybe I missed something. I should say sorry for that. Yeah, but there are not too many spaces, too many space on this slide. Sorry for that. So, talking about the code, we have a constructor that returns a copy of article struct. You can see it, but you can see it in line 7 where we're trying already to create it, right? So it only contains 2 fields, names and views. Just a small reminder that everything in Go is copied during passing between different functions. We read that rule before, right? We also print pointers of a variable in each function, right? We run this application, and what do we see here? Variables have different addresses. That means that value was copied between different stacks. Because if that were the only shared value, we would see the same pointer, right? But we see it different. This means that there were a few memory allocations for that. In our case, after new article function returns, it copies the value of a to a variable in main function. Then we run escape analysis and see that following output. As you can see, we see nothing here, right? This means that there are no values that escape to heap. Everything was stored in corresponding stacks here, right? We have a visual presentation of it as well. So we have a stack per goroutine. Each stack may have many memory segments. So each square is like a memory segment. And one segment for one function call. Once main was called, a first segment was created, this one, then execution flow was passed to a new article function and second segment was created, so from top to bottom. This segment will be marked as invalid, I'm talking about this specific segment, once new article function returns. That memory then will be not available to any other functions within the stack, like this one, but this is just imaginary. Anyway, you can learn more about it by reading, for example, I think the best resource is Arden Labs material, so I highly recommend to read them, and I also use them in preparation to this speech. Coming back to our topic, right? So address memory used by article value in these are different too. That proves that value isn't shared but is copied, right? And heap is still empty. You can see it here. Even if it's not fully clear to you right now, just please keep going, and I think it will be much better till the end of the presentation because we will review much more examples there and you will understand that. So pointer semantics, another example. We have the same code. The only difference that we now returning a. Let's take a look at what we see at the terminal. So addresses are the same. Escape analysis tells us that something not easy readable, yeah, if you're looking first time at it, yeah, but the last line is clear. Like we see A moved to heap, right? That's a decision. Please pay attention to the diagram we have here, right? Addresses in new article and main stack segments are the same. You can see this one and this one, right? However, we can point to the memory on a stack segment that is below. So this value is accessible from main to new article, but it's the same pointer. So if it would be allocated on stack, then we wouldn't have an access from main segment to new article segment. So the value should be allocated on heap because we need it to be accessible. This allows to access this address from different segments or even stacks itself, right? It may be not clear why we can't point memory from the segment below, yeah? So why we can't store something here and to be able to access it from this segment. It's easy because if we do so, once new article function returns, this one, right, its memory segment will be marked like as invalid, like this one, so it will not be available to us, and then it wouldn't work at all. So there is no any other option. If we need it to be available from segments higher, we have to move it to heap. Okay, indirect access, another case. As I've said that we can't point to the memory segments below, but can to the segment above. Here is an example exactly about that. We pass in a pointer to article to increment views function. There we are incrementing its value. That's it. Our function doesn't return anything. I hope the code is clear to you. And we see that addresses here are the same as in the previous example. So is this value allocated on a heap, right? Because in the previous example, that tells us that, yeah, it was on the heap. But no, escape analysis tells us that nothing escaped to heap, as you see, yeah, and it can't lie us. At least I hope so. So it may be not clear, understand. This example shows us something called like a side effect. Look at the diagram, please. So article value was located on main segment and shared down to the second segment. When increment views is executed, a segment above is valid and available. So it was created here, and then we tried to access it from here, right? When we're trying to access it from here, this segment is valid, it exists, right? And there is no problem to have this mechanism here. So there is no need to put it to heap. We can just keep it in the main and share it. Anyway, that's a bad example of code. I'm talking about this approach, right? You should not change data in function arguments whenever it's possible. It's much better to return a new value as a return argument here. Yeah. I hope now you understand what we are trying to learn, aren't you? We want just to know what code constructions makes our values to be allocated in heap. That's it. That's all what about escape analysis is. Because recall please, heap is pretty expensive, right? It's not cheap and easy to clean up. All right. Let's take a look at code, right? It's another example. Interfaces. We already saw this code. One change. Now we're using println instead of fmt.println. We see two different addresses here because article value was allocated in new function article segment and then copied to main function segment. So we have two pointers to function segments. Nothing escaped to heaps. I can't show you the diagram here right now because we have another example here. Like the same code, but the only difference is that instead of println we have fmt.printf in our case. We also see two different addresses, but they look a bit different. Please pay attention to these two. They are pretty close each other. And to these two, we see that the distance is too high, right? It should be in some different places, different locations of the memory. And escape analysis tells us that A, escape to heap, please pay attention, escapes to heap. Do you see these red phrases? Address of interface is converted, right? That is some kind of rules that we use to make the decision. A was moved to heap here because we have an interface conversion here, exactly according to this rule. The difference between println and fmt.printf in their arguments types. So second function accepts empty interfaces, and inside it some conversions are needed to do a right print, right? And the first one, println, accepts types that do not require conversions. What should we learn here is whenever we pass something to function that accepts interfaces, for example, that value is already a candidate for allocation on heap. There is no 100% guarantee for that because many other rules may happen as well, but chances are really high there, so we have to remember that. Maps. Let's talk about maps. What interesting can we find here? First case, we have a map with a string key and article as value. We map an article to a key A. What do we see? Escape analysis output tells us that map was allocated on stack and nothing escaped to heap. It happens because there are no only our main function. We have like the only function here. There are nobody who wanted this data as well. Let's take a look at another example. The only difference, we store a pointer to article as a value. You see, there are just a value and here a pointer to that value. Map is still allocated on a stack, but the article value isn't. it's allocated already on heap. That's due to a map literal value rule. You can see the rule here. All of them will be highlighted like this one, right? When you store a pointer to something as a map value, this value may be allocated on heap. So I'm talking not about the whole map, but exactly about this value, right? So to be 100% confident, it's the only way just to run escape analysis, what we are trying to learn right now. Because again, I'm showing you that in this specific situation, it is allocated on heap, but again, many different rules may be applied and it all depends on the code. Because if it's a very simple example of code like this one, it's easy to understand, but in production code where you have many things to do, many calls, yeah, you have to run it. Cool. Another example. I think this example is a bit underestimated, right? So we have an array of structs A with a length of 2730. So our array already contains this number of structs with empty values, right? According to the code you see. After that, we see that size of a struct and the whole array. Do you see it? Hope. A's size is 24 bytes, so 24 bytes is needed for a struct, a single a struct. 8 for integer field and 16 for string field. Array size, like the whole array size, is 65,520 bytes. You also can see the data. As we can see, everything is allocated on a stack. Even so, this array isn't a small one, right? It's a big array, like we have thousands of elements inside it. In the next example, we have the same code. Maybe somebody can find the difference. It should be easy, yeah. So right now, this array contains one more element, right? Just one more element. And its total size, as we can see here, is already 65,545 bytes. And escape analysis notifies us that array as a value is too large for stack. So you can see this rule, right? And what should we know? That not any size value can fit stack's size. Again, based on this information which we received. Here we can find a bit more information which can help us to understand what is big enough to be called on heap. Explicit variable declarations to be on a stack should be less than approximately 1 gigabyte of memory. I'm talking about this rule, right? If I'm not wrong, that's the maximal size of Go stack size. Like, I mean, 1 gigabyte is the maximum Go stack size in many operational systems. Yeah, but I may be wrong. On the right side, like we are talking about implicit variable declarations, to be on a stack should be less than 64,536 bytes. This one was allocated on heap. We just were out of limitations, right? We just required a bit more bytes than the limit is. After all, we have to pay attention to sizes when we work with optimization, right? Because in this case, like both sizes of arrays looks big, but this size is critical to us in our situation, right? And I think that's my favorite example, I guess. Inside foo function, we initialize a string slice A with len 0 and capacity 10. Everything is allocated on stack, as you see. Here we do the same, but with taking a capacity value from function argument. You should see it here. Because of that, the whole slice is now allocated on heap. And why? Because it's dynamic value for the scope of foo function. What I mean by this, like in this scenario, compiler can't 100% be sure what exact value will be here. Like it can be 10, it can be 5,000, right? And this affects the size of this slice. In some scenarios, it can be big enough to be allocated in stack, but in other scenarios, it can be too big for that, right? And you see, there is not so easy to make a decision because this value is dynamic, like this capacity is dynamic value. And compiler can determine that. That's why the goal is to avoid the situation when we allocated slice on stack and then we don't have enough available memory for there. So if compiler isn't sure about something, it makes the more secure decision. And like in our current situation, it's better to allocate it on heap and to be sure that we will not have any problems with memory limitations, right? So there are no more examples that I can share with you, and we have reviewed some of them, and I hope they were interesting to you. Yeah, let's make a short recall of cases we have went through. Yeah, so when it may escape to heap, right? First, whenever we need a value to be accessible from higher memory segments, please recall these diagrams we saw, right? From upper segments to lower segments. If function accepts interfaces and we pass some values there, so that's the case with fmt.printf and println in comparison. In case we store some pointers to values in maps or slice, right? So our map or slice elements are pointers to some values, but not the values itself. If our value is too big for stack, right? And whenever compiler isn't ready to make a decision because some data will be defined only in runtime, yeah, so we can't make the decision easily. We shouldn't think about these rules when we write the code from the scratch, right? Because there may be many rules and we need, like, we can learn some of them. It's really useful, but again, something might change in upcoming versions of Go. So we have to run escape analysis each time we really need to do any optimization here. And another point that's like, you have to start optimization only after your database works good and you don't have any problems with concurrency, synchronization, etc. So I mean, like, this is just one more instrument to find a bottleneck and to understand how to optimize it. But it's not please not overestimate it. Don't run it for really tiny applications. There is no sense for that. Yeah, so just a few words more before I finish. Here are my contacts in case you want to hear more from me, or you can give me any advices, feedbacks. I'll be happy for that. So you are welcome, you can reach me out. And also you can find a QR code on the right side that can be used for donation to support Ukraine in this terrible war. And I will highly appreciate that if you can do so. Thanks for attention. And I hope that really wasn't boring for you. I tried my best. Yeah, so I'll be happy to move to Q&A session. Thank you, everyone.
Здравейте, това беше темата на Виктор.
Благодарим на Виктор, макар и задочно, и се надяваме опасността при него вече да е преминала.
Да,